Hi guys, this is lesson 2 of our waves unit. Today we are going to talk a little bit about wave interaction. In our first discussion, we talked about different types of waves. We talked about mechanical waves versus electromagnetic waves. We also talked about the properties of waves, what characteristics they all have. And today we're going to start talking a little bit about what happens when they interact with either each other, another wave, or when they interact, when they run into different types of matter. So, wave interactions, the slide we're looking at right now. When a wave encounters a surface, when energy is traveling, because remember, waves carry energy, not matter. When energy is traveling and something gets in its way, so like let's say it's light from the sun and a window in your house gets in the way of that light, what happens then? So when any wave is traveling and something gets in its way, we've got 4 options here. We've got reflection, refraction, diffraction, and absorption. And if you're hearing a lot of background noise right now, sorry, I'm at my house and my dog is making a lot of noise. So if you hear anything, that's what it is. Okay, so like I said, reflection, refraction, diffraction, and absorption, all right there on the screen. So here is a diagram of each of those different words and what they mean. You can kind of pause if you want to and look at these yourself. I am going to talk about them in a little bit more detail, except for absorption. I want everybody to look right here at absorption for me. When absorption happens, it's really simple, so simple that I'm not actually going to talk about it in depth other than what I'm about to say right now. With absorption, the wave simply gets absorbed by whatever the surface is and it disappears. It's not there anymore. So, like a sound wave, if it hits maybe a wall and it can't get through the wall absorbs the sound wave, and then anybody on the other side of the wall doesn't hear it. So, absorption is pretty easy. But let's talk about these other 3. First, we've got reflection, and I think everybody's pretty good with this word. You understand what this word means. So when an object or a wave hits a surface through which it can't pass, it bounces back. So for example, a mirror. Light waves hit a mirror. They can't go through the mirror. So instead, because the glass is reflective, they reflect off. Same thing with an echo or a ball bouncing. A sound wave hits something, hits a surface. It can't go through that surface, so it bounces off, and we hear an echo. A ball bouncing. You throw a ball at something, it can't go through it, bounces back. That's reflection. And if you're looking at our picture here, you can see the difference between how things are reflected on a smooth surface versus a rough surface. So if your wave hits a smooth surface, it's going to bounce off nice and easy, same angles as it hit. But if it's a rough surface, you can see it kind of gets scattered all over the place everywhere. One other thing about reflection, there is what we call the law of reflection. And all the law of reflection means is when a wave hits something at a certain angle, it's going to be reflected off at that same angle. So if we go back to this picture here, on the smooth surface, they're all hitting at the same angle because it's just one flat solid surface, so they all kind of hit at the same point, so they bounce off at the same angle. On the rough surface, you can see different waves hit at different places. Some are higher than others, so whatever angle they happen to hit at, that's the angle they're going to bounce off at, and that's all that law means. Then we've got refraction. Refraction is a little bit different than reflection. In refraction, waves change mediums, and so they bend. Now remember, a medium is whatever it is that the wave is traveling through. So it could be air. Air could be your medium. Sound waves are traveling through the air. Or it could be water. Light waves are traveling through water. That's your medium. Or it could be glass. Whatever the case is, if it switches. So let's say that I'm talking, and the sound waves are traveling through the air and then they hit a wall. So they're traveling through something solid. Or light waves. Light waves are traveling through the air and then they hit a window, so they're traveling through glass instead. What happens is the wave speed changes. It can go a certain speed through the air, but it goes a different speed through the glass. So when that changes, the wave bends because it's not moving at the same speed anymore. So a great example of that is this picture we've got here. This is a prism. I'm sure you've all seen prisms before. They're just little glass triangles, right? And when a light wave is traveling through the air, like let's just say the sun, when it's traveling through the air, it tends to look white or yellow, right? When it hits the prism, it creates this rainbow, and here's why. You can see it happening. When the light is traveling through the air, it's going one speed. When it hits the glass, it refracts. Refraction is happening, and it starts going a different speed, and then it gets all split up, as you can see over here. It bends. It bends and changes, and then we can see all the different colors. Same thing if you put a spoon or a pencil or something in a glass of water, there's refraction here. So we are seeing the pencil right here through the air. So light waves are showing us what it's like in the air. But then those light waves hit the glass right here, and then they hit the water right here. And those light waves are traveling at different speeds through all three of those materials, the air, the glass, and the water. So when those light waves go through them and then they get to our eye, they're traveling at different speeds, which is why it looks bent. We're seeing this light wave at a different speed than we're seeing this light wave down here, if you're following my mouse. And that is refraction. The last one I'm going to talk about is diffraction. Diffraction changes the direction and the shape of a wave. So sometimes things get in waves' ways, and they have to travel around them. So when a plane wave passes through a small hole, diffraction will turn it into a circular wave. That's what's happening in our picture over here. So think about light or sound going in the crack underneath the door. So like you've shut a door, but there's that tiny little crack between the door and the floor, and sound waves and light waves can get through that. But like outside of the door, if you turn on a light, it's all over the place, but it has to go through just that tiny little crack underneath the door. That's going to change as it has to like get through smaller spaces, like we can see right here where I'm moving my mouse. Those waves will change direction and shape too, especially sound waves. Sound waves change shape pretty easily. Okay, so that's wave interactions, how different waves interact with different surfaces that they come into contact with. And that's reflection, refraction, diffraction, and absorption. And don't forget, I've got that slide at the beginning that has all four on the same slide. That's a pretty good resource for you. All right, so now let's talk about two more types of waves. In our last lesson, our first lesson, we talked about mechanical waves and electromagnetic waves. And the difference was mechanical waves needed a medium to travel through. They could not travel through empty space. They had to travel through air or water or something like that. Electromagnetic waves did not need a medium. They could travel through completely 100% empty space, which is why sunlight can get to us. Because light is an electromagnetic wave, it can travel through empty space. So now I want to break that down even further. We've got mechanical that needs a medium, electromagnetic that doesn't. But now let's break it down even further. So let's talk about mechanical waves. Mechanical waves that do need a medium, we can break those down into transverse and longitudinal waves. So let's talk about those. So a wave pulse is a short burst of a traveling wave. It's kind of what we see when we look at waves. It's easier to see wave pulses than it is to kind of look at a whole wave. So we tend to talk about wave pulses, which helps us understand how transverse and longitudinal waves move. So the oscillations of a transverse wave, those kind of pulses of the wave, they are not in the direction that the wave moves. Okay, and that's the difference between transverse and longitudinal, how they move. So in a transverse wave, it moves. We see we've got the beginning of the wave right here, and it's moving to the right. Okay, we've got this big arrow right here, if you're following my mouse, that shows you the entire wave itself, the energy is moving from the boy here all the way over to the right. However, the oscillations, those pulses, are moving up and down, right? So this whole wave is moving up and down. That is a transverse wave. The energy is starting over here with the boy, and I hope you're still following my mouse, and it moves all the way over here to the right. Okay, so that's the wave itself. However, the pulses are moving up and down. They are not moving left to right. They're moving up and down. And there's a graphic of that. You can look at this, pause it if you want to, kind of wrap your brain around that. So the wave is moving left to right. The pulses of the wave or the oscillation of the waves are moving up and down. We are actually going to do a lab tomorrow where we're going to pull out some slinkies and model this, and it's going to make a lot of sense when you see it. Hopefully it makes sense now, but if not, it definitely will tomorrow. Before we talk about longitudinal waves, though, I want to throw in right now Transverse waves. That is your vocabulary word of the day to send in and prove to me that you have watched the video before class so that you can go ahead and get started with the lesson when you get to class. So when you are done with this presentation and the question, what is the vocabulary word of the day? It is a transverse wave. So I want you to tell me how a transverse wave moves. Okay, longitudinal waves. Longitudinal waves are different than transverse waves. In a longitudinal wave, both the wave and the wave pulses move in the same direction, right? So here, again, we've got this wave still moving left to right, moving from the boy over to this wall, right? So are the pulses. And instead of moving up and down, the pulses are moving back and forth too. So what it ends up looking like is just places where, let's pretend it's a slinky, places where it's really close together, and then places where it's really far apart. And again, you're going to model this tomorrow with some slinkies, and it'll start to make a lot of sense. But what I want you to remember right now is transverse waves, the wave moves left to right, and the pulses move up and down. Longitudinal waves, the waves move left to right, and the pulses also move left to right. Just a little bit different. So here's that graphic again, only now we've included longitudinal waves, and you can kind of see how they work. So transverse waves, you can think of a water wave. The water is moving from way out in the middle of the ocean towards you on the shore, right? But the waves themselves, the water is moving up and down. Transverse waves are like a sound wave. The wave goes from me to you, and the pulses are also going from me to you. And I'm excited for you guys to do this lab tomorrow. You get to mess around with slinkies, but also it really does kind of show you the difference between these two waves. And just so you remember, transverse and longitudinal waves, both of them are mechanical waves. They have to have a medium to travel through, okay? All right. So that is it for your lesson today. This one was pretty quick and painless. Please don't forget to go ahead and as soon as you turn this off, go ahead on Google Classroom and send me your answer to that question so that I know that you're ready to go tomorrow. All right, guys, have a good evening or day or whatever time you're watching this, and I will see you next class.